Okay. So the format of the class is going to be a little bit different this time because the last class is a GE class, and it has a very strict syllabus that I have to get through. And so I have a certain pace that I need to hold, and I know people were, there was this intense focus on the computation of contour integrals because that's kind of what the first class is about. It's like calculus of complex functions. So the second class is really kind of a free-for-all, like, instructor's free choice. And so what I'm going to do in here is I'm going to walk you guys through some important areas of complex analysis, not in any one of them in a super deep way, but sort of connect out to theoretical math, applied math, and applications in engineering and physics. So we're not going to do a lot of like hardcore applications. We're going to point out how this stuff actually gets used in practice. So what I'm hoping is at the end of the class you get a taste for why complex analysis is kind of one of these glue fields that is behind lots of other fields in pure and applied math. So because I'm doing it this way, the sort of thing where I give you weekly quizzes or sort of weekly quizzes and in-class exams don't really work anymore because I want to ask more interesting questions. This is still not proof-based, but the questions are going to be a little bit harder because to be interesting, they're just going to be more challenging to work on. And so my intention this quarter is to do homework assignments that I pick up. There'll be fewer problems, but hopefully they'll be more interesting. There'll still be a lot of supporting like computational type examples so you get a handle on what's going on in here. But like the exam, I'm sort of anticipating the exam is going to be a take-home exam this time, right? Because I want people to be able to take the time to look at this stuff and work through it without having a 50-minute time limit like sitting over the top of them. There's probably no way I can get around having a final. So this is sort of one of the parts of the deal, but we'll talk about that more when we get there. So what I want to talk about this quarter, I've got three big areas that I want to talk about. So I want to talk about a subject called conformal maps. So conformal maps are maps that preserve angles. They show up in application in things like the study of the flow of vector fields in the plane. So in sort of 2D fluid dynamics, you see conformal maps be used. They show up in the study of topology. They show up in algebraic geometry. Part of conformal maps we'll be talking about will be transformations called the Mobius transformations. I'm just throwing words out here in case you've seen this in your context. I'm going to give the Riemann sphere and Riemann surfaces an adequate treatment here. And then the second sort of big area that I want to talk about is special functions. So for special functions, all right, what's the function that extends the factorial function? The gamma function. So we'll talk about the gamma function. And what's the function that's the subject of the Riemann hypothesis? Zeta function. I'll talk about the zeta function. And as part of this, I will also have a lecture on that. I know I have to do it, right, on this. Like what the hell that means, where it came from. If you've never seen the number file video that, like, I mean, nothing on math on YouTube is huge, but for the math world, this caused a big stink when this video came out. So if you're curious, you want to get a head start here, you could go watch Numberphile's video on this result and see. Don't watch any of the rebuttals to it. Just see if you can figure out all the mistakes they made. That's like, and then we'll talk about, when we get here, we'll talk about what this means. There is a sense in which this has meaning. And then the third area, I've sort of played around with a couple of things. I'd like to talk about complex dynamics. So complex dynamics, you've seen pictures of before. Every picture of a fractal you've ever seen comes out of complex dynamics. It's the idea of taking an analytic function and feeding in a point, and then feeding that point into the function itself. So you iterate the function on itself, and you keep track of what happens to the points when you do it. So complex dynamics is properly a subfield of a subject called dynamical systems. If you've never seen a dynamical system before, you can think about a differential equation, but you pretend time is discrete instead of continuous. So it's just an evolving system. And so we'll talk about fractals. We'll talk about the Mandelbrot set, and Julia sets, and Fatou sets, and we'll draw pretty pictures. That's what we'll do in that part. But this is sort of a survey of some big areas. I mean, there's dozens of places where complex analysis links up with stuff, but this is sort of some classical ideas and some things that I think there's something for everybody in here, I think. Okay, so before I go on to, I guess we are not using, I might use the textbook for problems, like exercises this time, but I am writing my own set of notes this time, which I posted on the link to this. So I'm writing these as I go, so my lecture notes are just posted on a website. You can download these, it's easy to print. They're not in the discussion post. There were some people that thought that my discussion post last time meant that you had 500 hours of reading every week. That's not the purpose of the discussion posts. That's where I put examples to work through. So I thought I would formally separate the notes, which will be on the GitHub page, from the examples where we talk about like what's actually going on, which will be in discussion posts, and people can comment on that. Okay. Because I'm generating these as I go, it's like there may be typos, so feel free if you find typos to let me know. The textbook for this part of the class, if you want something to refer to, this is a standard textbook, by the way, with all the implications of what I mean when I say this is a standard textbook. This is Marston and Hoffman. So for section 1, if you want a reference that's not just my notes, you want more detail, you want proofs. I mean, I will be typing examples into my notes too. But if you want something to refer to that I'm using to sort of guide this part of my lecture, it's Basic Complex Analysis by Marston and Hoffman. Marston and Hoffman. At any complex analysis book will be a good reference. This is just the one I'm following for this section. And as I use new references, I'll let you know where I'm getting them from. Okay, so any organizational concerns before we kick off with doing some math today? Anything I can answer? Thanks. Yep.
Is that book going to cover all of these things?
No, so I'm going to use that book to talk about these things. And actually, when I do the Riemann sphere, Riemann surfaces, I might have to use a different source to pull in there's some topological and algebraic ideas that show up here. So anything I get like that, like already like in my set of notes, I've got things like some dude's blog post because it has nice pictures on it. So like I'll give you a running list of the references that I'm using. So this is actually just a good book because it will basically cover everything we do except for this. And here I have a completely different set of notes that I use to teach a Frost project on like complex dynamics. That's a really nice introduction to what's going on here. Yep.
So theoretically, the notes that we do in class should be sufficient enough.
The notes in class? Yeah, I mean the idea is so what will be required basically. What I'm going to talk about is what I've written, and I may be the case that it occurs to me on like today on the way in, I thought, I should add another example. So your notes may actually be a little bit richer than what I've got typed up because I might have additional ideas, but I'm going to do my best to go back and put those ideas back in when I finish. So yeah, you don't need to buy anything for this class, which I got yelled at by the bookstore rep that was like, why haven't you adopted any course materials? Like, I don't know. They don't want to spend money? Yeah.
Is anything that we're doing this quarter, besides basic understanding of like a complex plane, built off of like residue theory and stuff like that?
Intrinsically in the background it all is, because the properties of analytic functions, so yes, in the sense that what we're going to be relying on constantly is the fact that differentiability and analyticity are the same thing, right? The sort of holomorphic analytic connection. And we will often refer to Laurent series when we're talking about certain kinds of, so one of the first things we're going to do is the Mobius transform is a rational function. So the natural setting for this is like rational functions which have poles, right? So And then down here, we're gonna revisit contour integrals down here because I'm gonna show you guys a way that you can use, as a motivation for studying the zeta function, I'm gonna show you how you can use contour integrals to do infinite summations. So an infinite sum is really an integral, right? I mean, there's no such thing as, integrals and sums are the same thing. It just depends on how big the pieces are that you're adding up. So there's a way you can trick an infinite sum into an integral and then cheat using complex analysis to add series up. So yeah, we'll see that there. And then probably not much of it over here because this is more the study of polynomials and again rational maps, but not super deep. So, but all the effort that we put into building the machinery of rational functions and Laurent series and Taylor series is always going to be running around in the background. Anything else? Okay. All right, let's do some math. I'll have a syllabus because I have to modify the syllabus for the last class was basically a modified calculus syllabus because of the way the last class has to be taught. I'm not doing that this time, so I have to give you guys a new syllabus. I haven't posted yet, but I will get it in. That reflects how the grading will be this time. Okay, so let's start with the function. Let's start with an example. So let's look at the function f of z is equal to z squared. So one thing we didn't have time to do last quarter was talk about how you visualize what one of these things is doing, right? So it was in the book that we're using sort of did it in passing, but I might want to know something about how this function is acting on its domain. It's hard to visualize things in 4 dimensions, right? If you think about in real dimensions, this function takes in a 2-dimensional object and spits out a 2-dimensional object. So if you really wanted to visualize it, you've got some sort of surface, but it's sitting in R4, and I don't know how to visualize that. So there's another strategy for thinking about what this thing is doing. And what you do is you imagine that you have sort of a domain copy of C, and you have a range copy of C. And instead of trying to track a graph, what you're going to do is you're going to look at what the function does to single points or little sets instead, or curves through points. So imagine that we're looking at the point, say, 1 plus 1i. Then we apply f to that. Where do we land? Well, that's pretty basic, right? Because what is 1 plus 1i? 1 plus 1i in polar notation is root 2 e to the I pi over 4. I think. So if you square that, then you get 2e to the I pi over 2. That makes sense? So all I've done here is I'm just taking root 2 e to the I pi over 4 and squared it to get root 2 squared, which is 2, and e to the I pi over 4 squared, so I add the exponents to get e to the I pi over 2. So this point under f gets mapped to a point on the imaginary axis of radius 2. That's not very interesting, but that's 2e to the I pi over 2, or if you like, 0 plus 2i. So more interesting is not just what f does to points, but what it does to things like curves through the point, or sets that that point is part of. So the next thing I want to try to visualize is what happens to f as it passes through, so let's say lines that pass through the point. So let's look at what f does to a couple of lines. So first, we can look at, say, the line. So we'll do another visualization here. It's the same point, 1 plus 1i. We already know 1 plus 1i gets sent up here to 0 plus 2i under f. So let's suppose that we just take this horizontal line right here. So that horizontal line is, this is a good question. What is the equation of that? This line right here in the complex plane has what equation? It's a curve, so it's going to be a parametric equation. So what's the parameterization of that line? What's that?
T going from.
Yeah, so normally you got to give your function a name. So we used C or gamma in the last class, but yeah, exactly, right? Gamma of t is equal to t plus I. If you like, you can think about this as being related to the R2 version, which is t comma 1. X coordinate t, y coordinate constantly equal to 1 gives you this horizontal line, right? Okay, so what is the image of the line under the graph? Because f doesn't just take points to points, it distorts the sets that you feed into it, does stuff to it. And the study of what functions do to curves they're acting on is an important part of analysis, broadly. Well, so this is a computational exercise. And the computational exercise is just to calculate, okay, well, f of z on gamma, so f of gamma of t is equal to f of t plus I, which is t plus I squared. Now remember, the goal here is that I want to plot this image in the other plane as a parametric function. So what I'm going to do is I'm going to multiply this all out, hopefully correctly. I think that's right. And now what I'm going to do is I'm going to sort it into its real and imaginary parts so I can plot it as a parametric function in the range copy of Z. So this is equal to t squared minus 1 plus 2ti. That may not look like something that you can plot, but remember, secretly we're allowed to think of this as an x-coordinate and this as a y-coordinate. So we could say x, which is, remember, the real part of f of z, is t squared minus 1, and the imaginary part of f of z, which I think of as a y-coordinate, is equal to 2t. Well, now what? Now you draw on your deep knowledge of calculus 4, calculus 3. Got parametric equation, x, y, and t. How am I going to graph it? Picking a t will give me a point. So you could, yeah, you want to do a table of points? You're welcome to do a table of points. What if I just wrote this graph down right here, just independently? Imagine complex analysis doesn't exist. I write down that graph, and I tell you that x of t is equal to t squared minus 1, and y of t is equal to 2t. What do you do in a situation like that? Yeah? You eliminate the parameter is the name of the technique, right? You can solve this to eliminate t. So if you say, well, that means that y over 2 is equal to t, then you can substitute this equation back into this one, and that gets you x is equal to y over 2 squared minus 1. So x is equal to 1/4 of a y squared minus 1. And again, this is the relationship between the real part of f of z and the imaginary part of f of z. What sort of object is that? What sort of parabola? Kind of like, what's 1/4 y squared minus 1. So we're shifted over here, and then I guess we kind of come through like this. Does that make sense? So I'm cheating a little bit because I'm not trying to be super accurate, but the idea here is this thing has an intercept at, do I have it open the right way? -1.
Yes.
Do I? -1? Yeah, it looks right to me. Yeah, so we slide it to the left by 1, and it opens to the right because the y squared is positive. Okay. Okay. So I'm going to add one more complication to this picture, which is what happens to the other axis. I've sort of drawn kind of a little x-axis that goes through the point right here. So let's actually keep track of what happens to the other one. And we're going to make an observation about what we see when that happens. So if instead of doing this, I look at this line, I'll bring colored chalk next time so I can separate these things. If I look at the second line, Well, if I parameterize that guy, it's going to look like gamma of t is equal to 1 plus it, which is going to give us f of gamma of t is 1 plus it squared, which is 1 plus 2it minus t squared, I think. Is that right? So I get 1 minus t squared plus 2it. And if you go through the same process, where you let this be equal to x, and you let this be equal to y, and you solve by plugging in, I think this time you end up with x is equal to 1 minus y over 2 squared, which is x is equal to 1 minus 1/4 of y squared. So that is a parabola that goes through this way. Right? So it shifted to the right, but opens to the left. Now the observation that I'm trying to, that I want to make here is if you calculate the derivative of these functions at that point, what you're going to find is these angles were right angles because we made up a little axis there. If you calculate the vectors that are the derivatives of these functions here, and I didn't do a great job of drawing this first one, because what you're supposed to see is that this tangent vector and this tangent vector remain at right angles. So the curves started crossing each other at right angles. And even though f distorted those lines, it did some crazy thing where it like took the plane and it twisted it, it sort of curved things, right? It curved these things this way and bent stuff. But the angle of crossing of those two curves was preserved. And that's a property that's actually true in general of analytic functions. So the observation that I want to make here is that f took a right angle crossing of two lines, and it spit out a right angle crossing of, I guess, the image of the lines. And so that's actually, yep.
Just a quick question. So there was like one crossing of those lines before F updated, and now there's like two places where
Yeah.
those lines crossing. Are both points where they cross gonna have the same angle of crossing as the previous one?
Okay, so what I'm gonna say here is that that's a good question. The answer is that we're only allowed to look at these things locally. So these are the behaviors that we're describing are not global behaviors; they're local behaviors. So this line and this line cross up in this way at this point. This crossing over here reflects the fact that z squared is taking the plane and twisting it over itself. So because it wraps it around itself twice, and that's why the curves wrap and touch each other. We'll get into like why that's happening later, but you should think of what we're describing right here as there's a little tiny window around the point that we started with, and we look at this sort of stretched little window on the other side, and we're just restricting our attention to local behavior. So in general, when we're dealing with complex functions, we don't think about global behavior. We think about local behavior. It's very difficult to say things about global behavior of functions. And you saw that in the last class because we were describing power series at points and differentiabilities and neighborhoods around points. So it was always working on neighborhoods. We hardly ever said anything about what was happening globally on some, like all of C or something. So yeah, no. You should think this has some kind of meaning that I'm not going to talk about yet because this actually this would be more a representation of what the function does to the entire plane, but it's hard to. I'm going to show you why that's hard to interpret. A good question. Okay, so the fact that we have right angle crossings to right angle crossings is the heart of our first big definition here. So a function, okay, I guess because of the nature of the math in this class, let me remind you guys what a domain is. So a domain is an open, connected subset complex plane. And really secretly, if you've seen any topology, it means that you can get from any point in the set to any other point in the set with a curve. Connected is not generally equal to path connected, but an open connected set is path connected. So this really means any point in the domain is connected by a path to any other point in the domain. In the domain. That's the least we ask of the domains of our functions, is that we can get from one point to the next, because we want to be able to do stuff like draw contours like this between points. All right. So a function from a domain A to B is called conformal if for each point in A, f rotates tangent vectors to curves through Z naught by a fixed angle. Theta, and stretches tangent vectors by a fixed stretch factor. So a conformal map is one that rotates tangent vectors to curves by a fixed angle. That's actually why they end up preserving right angles or any other set of angles between two lines, because if both of the tangent vectors have been rotated by the same theta, if they started at 90 degrees, they ended at 90 degrees. Okay? And they stretch the vectors by a fixed factor r just means that these might not be the same size as, like, if you have little tangent vectors here and here that are unit vectors, they might not stay unit vectors, but both vectors got stretched by the same factor. If you know anything about if you guys have spent some time in linear algebra studying matrices, this should seem familiar to you, right? That this has the flavor of a linear algebra idea, like a rigid rotation. Yep.
Is this like an isometry?
Oh, it can't be an isometry because it could stretch.
Okay.
Right? So the metric is going to change. So you should think instead it's never mind. I was going to drift into esoteria for a second there, but it's not going to make anything more clear, so we'll stay away from that. I can tell you what sort of matrix action is happening in the background of the class if you want.
Okay.
Okay, so the question is why? What is actually happening here? And what are the conformal maps? We put in Z squared. Z squared seems like it has the property because by the math student's argument that since it happened once, it must happen forever. Proof by special case, right? So here's kind of a striking theorem that gives us a rich library of examples of conformal maps. So let's let f from A to B be analytic. And let's let f prime of Z naught not be equal to 0 for all Z naught in A. So I have a function on a domain with a non-vanishing derivative. Then f is conformal. So every analytic function on a place where its derivative doesn't vanish is a conformal map. So last quarter, you may have heard me refer to analytic functions as rigid in their behavior, and you may have confused why I use the word rigid. What this means is that away from places where the derivative vanishes, all that an analytic function can do is rotate and stretch at a point. Which means circles locally turn into other circles locally with a different radius is one way of thinking about it. It's not quite that, but like that's what you should think about it. This is a highly restrictive condition for a function to have. Yep.
So like there's a fixed angle and a fixed scale factor for every single point?
Yes, and it varies by point to point, yeah.
And does it vary like continuously?
It does actually.
Okay.
Yeah. Yeah. I mean, this like analytic functions are like hyper-continuous is a way of thinking about it because this is going to be related, those factors are going to be related to the derivative, and the derivative is continuous because the function is infinitely differentiable and all of the derivatives are continuous. So yeah, it's like this is why complex functions get used in applications, is because anything you do to them preserves continuity basically on the interior of the domains. Okay, so why? Why do analytic functions have that property? So it's insulting to call this a proof. So let's just assume that we have a point z naught, and we have some curve gamma of t going through it.
Good picture.
Yep. There you go. And well, I'm actually not going to do a proof by picture. I'm going to do a proof by calculus 1. So here's the proof. Let sigma of t be equal to f of gamma of t. Since we're in the second complex analysis class, we could use a new Greek letter. Then gamma prime of t is equal to, well, the chain rule says this is f prime of gamma of t times gamma prime of t. And let's actually, we can always normalize this function so that gamma of 0 is equal to z naught. So we'll just let this be this, we'll let this curve pass through z naught at the point t is equal to 0. You can always choose that. So gamma of t is a curve, it passes through z naught, and also gamma of 0 is equal to z naught. Sigma is the composition of f with the curve. So this thing, the words for this is the image of gamma under f, is the way that you would refer to that object. Well, what's gamma prime of 0? It's f prime of gamma of 0 times gamma prime at 0. But f prime of gamma of 0 is f prime of z naught. That's fixed. It didn't matter what gamma we put in the beginning. We took gamma in the beginning. The chain rule says that evaluated at 0, we get the derivative of gamma, which is the original tangent vector, multiplied by a fixed complex number, f prime of z naught. And f prime of z naught can be written r e to the I theta times gamma prime of 0, and that's where the stretch factor comes from, and that's where the rotation comes from. So the derivative of f is what controls how this rotation is happening. Notice, this is independent of the choice of curve through z naught. So any curve I drive through z naught, for computational convenience, normalized this way, will always be rotated and stretched by the same f prime of z naught. Yep?
So gamma prime of 0 there, that part is the tangent.
Yeah, so you could think of this is gamma prime of 0. It's the tangent vector of this curve as it passes through the point. And so what's happened is the gamma prime of 0 from the domain picture, all that gamma does, all that f does is it looks at its derivative and then rotates that vector and stretches it by whatever the size of the derivative was. Okay? Yep.
Was it possible to be complex differentiable only a couple times?
No. Complex differentiable is a condition that is defined on, so yeah, let's remind ourselves about that because that's an important point. So the big idea of complex differentiability and why this is so important is that complex differentiability is on a neighborhood of a point. So you always have an infinite number of places where things are differentiable. So if you're differentiable at z naught, it means really secretly there's an entire disk of points on which your derivative exists. So you can always slide, this is why the whole thing even worked, was we set up our definition of differentiable to mean not just differentiable at a point, but differentiable on a little disk around the point. And so what that means is, if you started sliding around z naught in different directions, this number might change, but each point you get to, this changes continuously as you move off of z naught places. This is predictable behavior. So this is a point-wise condition. Oh, yeah. Let me be more clear. Complex differential is defined on open neighborhoods of points. Okay, so the idea is we always have behavior on some little disk no matter what. And the upshot of complex analysis 1 is that you're differentiable exactly where you're analytic. So basically you look at a function, you figure out where its closest singularity is, and you're differentiable everywhere out to that singularity. So the singularities of the function dictate when differentiability stops. Okay, so what's the problem with what we did right here? Like, when does this formula break down?
Away from zero.
What do you mean?
Oh, like away from the point in the curve.
So, I mean, yes, but you could, intrinsically what you could do is you could move over a little bit. I mean, is there a case in which I can't make this argument? There was a condition in the theorem, right, which was that the derivative was not equal to 0. Why is that in there? Well, if f prime of z naught was equal to 0, this chain rule formula tells you nothing, right? It's like the f ate all the information about gamma up, because when you took the chain rule and evaluated it, you have no idea what gamma prime of 0 is. Because if that's equal to 0, it destroys anything that you know about gamma prime. So this part is there because if this was equal to 0, you'd be multiplying 0 times gamma prime and you get nothing. Yeah.
So would zeroing out, I guess, in the image not be a stretch or rotation?
Well, let's see. Let's look at our old friend f of z is equal to z squared. I know a place where the derivative of that function is equal to 0.
At 0?
Yeah. All right, so let's look at what happens. So f prime of z is equal to 2z. So f prime at 0 is equal to 0. So let's look and actually see what happens at what f of z is equal to z squared does to a couple of lines at the origin. Okay, so there's 0 right there. Here's 0 right here. I think it's pretty clear that f sends 0 to 0. What does f do to the real axis? Let's see. If our curve gamma of t is just equal to t plus I times 0, that's not theta, that's the sort of x-axis through 0, 0, right? This is the real axis. Well, f of gamma of t is just t squared. So this line right here, which is gamma of t, ends up being sent to itself. Right? These were, in fact, not even that. It's like just the right version of it or something, right? So these guys were all real. So these guys are all real and positive. That's already weird. So instead of line to a half line, what happens to the imaginary axis? Well, the version of the imaginary axis, that's a good extra letter. Oh, how about this guy? That's a funny letter. 0 plus it. That looks like, that's this. Maybe I should do it like this, so we can distinguish the two. That's this line, right? I've parameterized the imaginary axis by doing this, where t runs from minus infinity to infinity. So f of, what is this, capital C, is equal to it squared, which is minus t squared. Oh. So that didn't preserve angles. That took the whole x-axis and pushed it into the right real axis, and it took the entire it took the entire imaginary axis and it spit it out on the real axis pointing the other direction. So this did not preserve angles, because the original angle here between these two lines is pi over 2. Now that angle is pi. So it's still a well-defined operation. F is still analytic. I can still track what happens to the image of F acting on these things. But we do not get the same sort of rigidity condition. Weird things can happen in places where the derivative is equal to 0. Yep.
Are there potentially special cases in which f prime z naught isn't 0 and it would work?
What do you mean?
It would be conformal? Are there like special cases?
If f prime was 0 but also was conformal?
Yeah.
Oh yeah.
Okay.
Yeah. So, and we'll look at a family of those too. But for now, what I want you to think is, anytime we have a big behavior that works almost everywhere except at one class of points, then usually we give it a name indicating how terrible those points are and that we should stay away from them. So, any point z naught at which f prime of z naught is equal to 0 is called a singular point for f. Not a singularity, but a singular point, right? So singular in the sense that you might ask, well, why use the word singular? The idea is that the derivative of f for an analytic function, that can only happen at a point at a time. You can have a whole curve where things are flat. It can happen at points. And so at those points, you have to be careful. So if you want to imagine what z squared is actually doing, it looks at the complex plane and it sort of unfolds it. And everywhere except where the unfolding is happening, it's very rigid in what it's doing. But at that one point where things are rotating out, the angles can't be preserved, because what z squared does is it doubles angles. But it doubles angles with respect to the origin. So the origin is where that unfolding or rotation is actually happening in the function. So aside from this one bad spot, this is a conformal map. Yep.
Why do singular points occur singularly?
So you can. It turns out to be the case that if an analytic function is 0 on a line,
It's constant.
it's just constantly 0. You can't have analytic functions that like take on single values without being that single value everywhere. It's a consequence of the maximum modulus principle, it turns out.
Would a constant function not be analytic then?
Well, that's what in these theorems what you always say is like aside from constant functions, right? I mean, constant functions are trivially conformal, right?
Sure.
So yeah, their derivative is equal to 0 everywhere, but they also, what does a constant function do? It looks at the input and leaves it alone except for multiplying by a number. So yeah, those are conformal everywhere. Right, so the idea is that, just to make clear what this example is about, this point was a point at which f prime of 0 was equal to 0 and f is not conformal at 0 because it didn't preserve the angles of the curve that we fed it. Okay. So what we're going to do next, next time, I guess. I mean, I've got 5 minutes left, but I'm not sure that I want to push any further. So I'll ask one last question for the day, which is, way back in Calculus 1, you guys learned a theorem that describes the relationship between the derivative of a function and the derivative of its inverse. You may remember it as a formula involving fractions and inverse functions. I'm just curious if anybody remembers what that formula says.
invertible, and
Assume f is invertible. I'll give it to you. I'll give you f is invertible
differentiable.
and differentiable. I want to know like what the if I just wrote down you have f of z is equal to w, and you have f inverse of w is equal to z, and I write down f prime, I say d by dw of f inverse of w. Something goes on the other side of this equation involving f. It's this trick that you get to use where you can use the function to find the derivative of the inverse.
So 1 over
The derivative of f at z.
Does anybody remember that? This is one of these things that just gets blown through in passing when you take calculus. So what this formula describes is the relation, what's striking about this formula is that the derivative of an inverse function and the derivative of a function are related to each other with this reciprocal relationship. Now it shouldn't surprise you, by the way, because if you actually think about, let's just suppose we're back in regular old calculus, and you have a function and its inverse, and you calculate the derivative of the function at a spot like this right here, and it has some slope. Well, the inverse point is this point right here, and it has this slope. That there's a relationship between these, right? These are reciprocal relationships. There, proof by picture that formula is true. So what we're going to do next time is we're going to talk about the next feature that we want to bolt on to conformal maps. The whole point of conformal maps is that sometimes I have a problem set up on a domain that sucks, or the functions are terrible, right? I don't know anything about the functions. So what I can do is I can cheat by taking my original domain and changing it into a nice one. Oh, I've got some blob over here. I don't want to work on a blob. I want to work on a circle. So if I could figure out a way to conformally map my blob onto a circle, then I have a nice regular domain that I can solve my function on. This comes up all the time in engineering disciplines. The question is, I can only do that if I can go in both directions. If I have some blob, and I want to turn it into a circle, and I want to do that conformally, so that if I'm at some point and I've got two lines crossing through each other, and I come over here, and those two lines still cross at 90 degrees, this will only be useful to me if I can conformally map in this direction, and then that has an inverse that lets me get back to the original problem I was trying to solve. So what we're going to do next is we're going to talk about bijective conformal maps, or invertible conformal maps. So it's that's the feature that really makes these things useful for problem solving generally. Like the geometry of preserving angles means whatever your physical problem was over here, it stays the same physical problem over here basically, because you haven't changed the geometry. And if we had invertibility, it would mean, boy, this problem is hard to work on this blob. Let's move to a circle and solve it, and then just undo that map to get a solution to my original problem. So invertibility is the next thing we'll add to this. And then we'll talk about a special class of conformal maps that show up all the time in the study of the disk. All right. I will put some more examples up online this evening. Thanks for coming. I'm looking forward to this one.